Here we have a few questions that will help us review some of the reactions we learned about in this chapter. The first reaction shown is a ketone reacting with sodium borohydride or lithium aluminum hydride, followed by aqueous acid. In the next reaction, we have an aldehyde reacting with an organolithium or a Grignard reagent, followed by aqueous acid. The third reaction involves mercury diacetate and water. In a second step, sodium borohydride is used. Alternatively, we can use a mixture of sulfuric acid and water to do the same reaction. Fourth reaction shown here is an alkene under hydroboration, which is using borane followed by hydrogen peroxide and sodium hydroxide. And then lastly, a secondary alcohol is mixed with chromic acid, whether using chromium trioxide or sodium dichromate to do the reaction. First reaction on this slide, we have a ketone mixed with sodium borohydride or lithium aluminum hydride. Both reagents provide a hydride, and then that's followed by aqueous acid. The overall result is that the carbonyl will be reduced into an alcohol. In the second reaction, we use an organolithium or Grignard reagent. Both contain an ethyl group. That ethyl group will be transferred to the carbon of the aldehyde. The attack will occur at this carbon, and then the carbonyl will be turned into an alcohol that contains an extra ethyl group. In the third reaction, we have a double bond that reacts with mercury diacetate and water to add an alcohol to the more substituted carbon and a mercury acetate group to the least substituted carbon. When we follow that up by sodium borohydride, the mercury acetate group gets converted into a hydrogen. Overall, we convert the alkene into a Markovnikov alcohol. We can do the same reaction with sulfuric acid and water, which will produce the same product. Using this alkene and borane followed by hydrogen peroxide and base, we will convert the alkene into the anti-Markovnikov alcohol, where the alcohol adds to the least substituted carbon, and there will be a hydrogen added to the more substituted carbon from the same side as the alcohol to its in addition. That leads to the ethyl group that was previously on the alkene being trans to the alcohol. Lastly, this secondary alcohol will be oxidized by chromic acid into a ketone. In this slide, we have a primary alcohol that will be oxidized with chromic acid. In the second reaction, we're using a secondary alcohol to react with sulfuric acid and heat. Third reaction will involve a secondary alcohol and thionyl chloride. And a similar reaction is reacting a secondary alcohol with phosphorus tribromide. Lastly, we're going to take a secondary alcohol and react it with TMS chloride and base in the form of triethylamine. In the first reaction in this slide, we have a primary alcohol being oxidized by chromic acid. That will lead to conversion of the alcohol into an aldehyde initially, which will then be further oxidized into carboxylic acid. In the second reaction, the secondary alcohol will be dehydrated with sulfuric acid and heat to give the cis alkene. The anti-cis alkene, which would form with this carbon or these sets of carbons, is going to be the minor product. In the third reaction, we have a secondary alcohol with stereochemistry facing up. If we react it with thionyl chloride, it will be converted into a chloride with the stereochemistry being down. In the fourth reaction, the same alcohol or similar alcohol, with the stereochemistry facing up, reacting with PBr3 will be converted into a bromide with the stereochemistry facing down. And then lastly, a secondary alcohol and TMS chloride with base will protect the alcohol as a siloprotectant protected alcohol in the form of TMS as shown here. In the first reaction, we have a primary alcohol being oxidized with PCC. In the second reaction, we have a tertiary alcohol reacting with ACl. And then lastly, this protected alcohol will react with TBAF followed by aqueous acid. A primary alcohol that is oxidized by PCC will be converted into an aldehyde, and that should be the end of the reaction. If we were using chromic acid, we would end up with a carboxylic acid. With tertiary alcohols, when we mix them with ACl, we convert them into a chloride. This is a fairly quick reaction when it's a tertiary alcohol. It is slower with secondary and primary alcohols. If we have a protected alcohol with TMS, if we use TBAF, the protecting group will be removed and we'll end up with an alcohol. Here we have a ketone that is going to be converted into a secondary alcohol that has a 1,2,3 carbon chain attached with an aldehyde at the end. For the synthesis problem, we have to compare the reactant to the product. Notice we're taking a ketone and converted it apparently into a secondary alcohol that has a 3 carbon chain attached with aldehyde and then. At first glance, it appears that we can use some sort of Grignard or organolithium to add the 3 carbons to the ketone and convert it into an alcohol. However, we have to be careful. Aldehydes are susceptible to reactions with Grignards and organolithiums, so we want to perhaps hide or protect this aldehyde first. If we add Grignard that has 3 carbons and also a double bond within the 3 carbons, we can add the 3 carbons we need and also add a functionality that we can later convert into an aldehyde. If we do a hydroboration of that alkene, we should end up with the least substituted anti-Markovnikov alcohol, and then oxidation with PCC of this primary alcohol should convert it into an aldehyde. Note that this tertiary alcohol will not be oxidized since tertiary alcohols generally do not react any further. An alternative reaction that we might want to use is instead of a double bond here, we could have an alcohol that is protected with a TMS group and a single bond instead of a double bond. And then in the next step, we would want to use TBAF to remove the protecting group. And then lastly, we can do the same oxidation of that primary alcohol to the aldehyde.